right, good morning. Thank you all for being here on a Friday, and an extra special thanks to the conveners for the invitation. Before I dive into this, I wanted to, none of you are listening to anything I'm saying because I got this cool video on. Before I dive into this, I want to tell you a little bit about myself. So I'm a biochemist and physiologist. I was really interested in how matter and energy move through our biosphere, right? And we think a lot about these processes in the deep ocean, from microbes to animals. Now, for the last 15 years, we've been using the kinds of bioelectrochemical systems that Lori did a wonderful job of talking about in the context of thinking about how organisms might well, let's just say, partake in and benefit from bioelectrochemical reactions in these systems. And Lori, I may be throwing in my CV for your postdoc application. You guys are up to some cool stuff. In my lab, we've been using these approaches to study seeps and vents, and in particular, microbes that we think are engaged in some of these bioelectrochemical processes. The work I want to show you today is representative of the kind of work that we do in the lab. And the take-home message that I want to share with you is that all living systems are bioelectrochemical systems, and many of them, not all of them, but many of them have a kind of a unique diagnostic fingerprint that you can detect if you are interrogating them electrochemically. That being said, living systems are inextricably tied to and influence their abiotic environment. So a lot of what I want to share with you today is how we can use these systems to understand how microbes influence and shape their environment, and in turn, how their influence on that environment affects their activity. In the interest of time, I'll move through some of these intro slides at a quick pace because Lori set us up very nicely. So let's go ahead and get started. So as you all know, vents are some of Earth's most extreme environments. You know, you're talking about places where you have really high temperature, chemically reduced low pH fluids moving from the subsurface into an overlying cool oxic water column. Bear in mind that these fluids are enriched in hydrogen, hydrogen sulfide, dissolved metals, including arsenic, lead, zinc, and indeed many of the rare earth elements that Annalise mentioned before. Now, hydrothermal vent chimneys they're mineral precipitates, so you really can't think of them as being sort of consolidated in the way you might think of a metamorphic rock or an igneous rock. The way this starts is you have fluid flow that comes out of a crack, right, where perhaps you have tectonic activity that's reshaped the subsurface plumbing. As soon as you have that hot fluid emerging into seawater, you get the precipitation of anhydrite, right, this calcium sulfate compound. And eventually, over time, what seems to happen is that the anhydrite acts as a physical barrier between the surrounding cool oxic water and then the hydrothermal end member fluid, if you will. And you start to see the precipitation of metal sulfides. You end up with polymetallic sulfides. And as this assembly sort of thickens, you end up with, more often than not, chalcopyrite lining the inner walls and so on. Now, as mentioned, these are natural electrochemical reactors because you have the semiconductive and conductive matrix that separates fluids of different potentials. Right, so what you can measure this, right, as our colleagues Nakamura and others have done, and measure this potential where you can see through this porous chimney electron flow. You can also imagine that porous chimney is a fantastic place for microorganisms to thrive. A number of us have been working on this over the years, and we find that organisms that live inside these chimney walls are capitalizing on this electrical potential in any number of different ways. The way a lot of them do this is through microbial extracellular electron transfer, and I'm giving you a very simple cartoonish version of this. But the idea is that for us, we humans, we are, and forgive me, a little physiologically boring when it comes to our energy metabolism, right? You eat you eat the bodies of dead things, more or less, or whatever they may be. You breathe in oxygen, you move those into the inside of your cell and carry out metabolic reactions. EET is really about extending energy metabolism beyond the cell by having outward-facing redox active molecules that allow you to engage with the solid phase in your environment, say, for example, iron oxides, right? that you can use as electron acceptors. It's like breathing rust. Imagine putting your hand on a rusty plate and using that as your electron acceptor. Or conversely, taking up electrons from the environment through these redox active moieties that allow you to harvest those electrons and use them to do work. Bioelectrochemical systems are really useful in studying these kinds of organisms, and not only those, but for the purpose of this talk, we're going to focus on organisms that we think are engaged in EET. Now, one thing that's really interesting is when we think about chimney growth and we think about the fact that we know that chimneys undergo this mineralogical evolution, that you end up with this metallic sulfide matrix that's semiconductive. Now, there is a bit of a chicken or the egg question here when it comes to hydrothermal vent growth. Is it that you have this abiotic process where you have the deposition, if arguably the electrochemical deposition of polymetallic sulfides that create an environment for microbes, or conversely, are microbes that are capable of EET or engaged in EET participating in the formation of chimneys? So we've made a few different artificial vents over the years. The one I'm going to show you today is a high-pressure, high-temperature reactor. I've simplified this dramatically, in which you can imagine a high-pressure vessel in which you have a working electrode that acts as our site of nucleation, if you will, a place where we can start the deposition of anhydrite and polymetallic sulfides. Of course, that's a working electrode. Elsewhere, there's a counter electrode and a reference electrode. For simplicity, I've left them off. We can use potentiostats to poise these at potential. We can wire it so that we let the chemicals do the work, and so on and so forth. But again, in the interest of simplicity, what I wanted to show you is that we can irrigate this high-pressure, high-temperature vessel with hot anoxic vent fluid into an overlying cold oxic water column. There's a little picture of some of our artificial hydrothermal vents. And what we did is we then took these and we did a series of experiments. This is work done by Amy Gartman, who's now at the USGS, and Aude Picard, who's at the University of Nevada, Las Vegas. Did a series of experiments in which we set these up at different temperatures, different potentials, and so on and so forth. We then inoculated them with a modest amount of material from East Pacific Rise hydrothermal vents. Now remember, you're irrigating with vent fluid that's enriched in hydrogen sulfide and so on and so forth, and into an overlying oxic water column. And we started to look at mineral deposition on the electrode. We measured changes in geochemistry, both the volatile and dissolved and solid phase, and looked at changes in the microbial ecology on those deposits. Who was growing at what point in time and so on. So I'm going to give you some highlights here. We set these systems up so that to an extent they mimic the kind of tidal pumping we see at hydrothermal vents, which isn't quite, tidal, but the point is you see oscillations in the influx of sulfidic water and so on. And what's interesting is by measuring the current density on our electrodes, you begin to see that when we have a system in which we used our kill control, right? We gamma irradiated the sulfide deposits before we inoculated them. You end up with peaks as soon as you introduce the sulfide. This is abiotic sulfide oxidation on the electrode, where the sulfides actually oxidize to amorphous sulfur. And then you get a sort of a typical kind of Cottrellian decay and reach a sort of baseline here of very low current in an abiotic system. When you look at the black lines, what you see is that with every sulfide intrusion into the reactor, you reach a steady state where you have a modest bit of current production, and that continues to increase over the course of the incubation, which we took out to about 50 days. This is indicative of biological growth on the electrode, and we've seen this time and again, not only at hydrothermal vents, but at seeps and elsewhere. What was really cool, right, just to kind of get to the punchline here, is that we see striking differences in the rate and extent of mineralization in reactors with live microbes. That is to say, when you look at the deposition on an electrode in a reactor with a gamma irradiated sample versus that with a a sample with the live microbes from the EPR, you see really striking differences in metal sulfide deposition, primarily McKenna-white, and that you don't see on the irradiated sample. We do recover a few adsorbed microbes. These may in fact also be alive, right? I mean, gamma irradiation works pretty well, but we do see a few bugs here, and here you see this really extensive network of microbes interlaced with the polymetallic sulfides and anhydrite and so on, and about 10 to the 5th cells per centimeter squared. These nascent precipitates, as we start to look at this over time, we start to see some of the first colonizers being sulfate-reducing bacteria. Desulfosoma rather, which is a known electroactive sulfate reducer, as well as Deferribacter. Same thing, a known electroactive sulfate reducer. Are finding themselves associating with our electrodes. We saw increases in diversity over time, and ultimately you get the kind of organisms we typically see there: sulfate reducers, sulfide oxidizers, sulfur oxidizers, and even methanogens. So we're really starting to think about the deposition events now as being a kind of microbial mineral amalgamation. This is sort of our current model for how chimneys grow, and that venting fluids begin by depositing anhydrite, and then to an extent iron oxides. And this sort of forms a geochemical setting for the colonization by sulfate-reducing bacteria and some iron reducers as well. And you begin to get their growth on the surface, and then you start to see the enhanced production of iron-2 and sulfides and so on. And so you find that the microbes are really playing some role, probably far more complicated than what I've shown you here, in promoting the deposition of these polymetallic sulfides. Some of it may be specific. I'll show you one interesting example of that. Some of it may be non-specific, simply through the production of biomass or exopolysaccharides that may just facilitate this amalgamation. One cool bit of work came out of Ode's work, where she was studying some of these sulfate-reducing bacteria and was really interested in understanding the role they play in iron sulfide production. And this is a cool example of a sulfate reducer, Desulfovibrio, whose cells end up acting as points of nucleation. And this is really cool because we were able to show that we end up with iron sulfides forming on the outside of these individual cells, and in fact it's McKenna-white. This is a slightly different crystal structure than pyrite. Both are sort of thermodynamically favored under these conditions, but McKenna-white is more kinetically favored. And we end up with pyrite production thanks to ripening over time. But what's really cool about this is to also think about the implications for the microbes. Iron sulfides act as great sites for especially in the presence of iron, for the production of iron sulfides. This pulls down the apparent sulfide concentration around the cell, thus reducing any potential back pressure of sulfide buildup in and around the cell, right? So this is the extent to which that matters to sulfate reduction, we don't know yet, but we're really working on understanding, does this deposition of iron sulfides actually mean something for the energetics and the favorability of sulfate reduction by these organisms. So when we think about these bioelectrochemical processes, and you think about EET, as Lori mentioned before, right, this really helps these kind of so-called endolithic microbes access remote oxidants, and this should also say reductants, and it could be an evolutionary solution to living in what is a stratified world. In the interest of time, I'll not wax sort of poetic about stratification, but that is in fact the state of our world, that it's not just homogeneous. And so have this capacity of extending your physiological influence to beyond your cellular envelope, you could imagine being strongly selected for. EET also influences proximal and distal chemistry. One of the coolest things about, in my opinion, about this phenomenon is when you look at organisms that are using extracellular electron transfer, they're actually changing, they're kind of partitioning alkalinity in a way that eventually reaches a steady state, but it is at least over short time domains influencing chemistry locally and distally in differentially speaking. And it, in my opinion, reshapes our notion of how we think about anaerobic metabolism. Some of the organisms, they live in anaerobic sediments, but in fact, they are benefiting from access to oxidants that are at least on their spatial scales, rather distant. And so I'll just wrap it up by reminding us that all living organisms are bioelectrochemical machines, that we use chemiosmosis, right, to establish charge gradients to do work. EET microbes have biological features, outer membrane cytochromes and so on, even the production of redox-active small molecules that can be electrochemically interrogated and to a degree easily identified, right? This is a plot from some work we've done with Arpita Bose on photoferrotrophic microbes, in which we can use cyclic voltammetry to show the midpoint potential of some of the redox-active compounds on their cell surface that they use. But other living organisms, even if they don't do EET, are replete with redox-active molecules. And this is sort of kind of a new area of study for us and for others. But all living organisms are susceptible to sort of, let's call it electrochemical interrogation or detection. How much resolution we have or the specificity, that all remains to be determined. But the punchline here is that these kinds of electrochemical studies underscore this inextricable relationship between biological processes in their abiotic environment, especially in our electrically conductive world. Whoops, I did not mean to hit that button, but I'll end there. I want to thank you for your time, and I'll gladly entertain any questions.
Away from the vent itself, I mean, obviously the vent providing the anhydride and then that provides the initial physical barrier. But if the electrical current itself is detectable, how far away from the vent is that measurable? Do these communities extend out? In other words, I'm wondering in general how far these metabolisms might build from the vent out and occupy the sediments on the seafloor.
Yeah, that's a great question. So your question, you're asking how far out can you go from a vent and still sort of use this metabolic capacity to capitalize on this. So let's, in the interest of time, I'll say that the answer to the question is really a function of the scale at which we're talking. So for now, I'm going to focus on the sort of microbial scale. So this starts to become problematic when you move beyond the centimeter scale. Just to sort of, in other words, I don't think you should be imagining microorganisms a kilometer away being directly electrically sort of connected, if you will, to a vent. I think that's improbable. And a lot of it really has to do with resistivity, even in a wonderfully conductive solution like seawater. So this is really relevant over this, I think, centimeters. Maybe we're pushing, tens of centimeters or a little bit more. Although I think one thing that's important to think about is that this is also relevant in sediments, because sediments themselves are conductive to varying degrees due to humics and other compounds. And so in sediments, we also see the same phenomenon. So I don't want to leave you with the impression that this is only relevant in vent systems where you have semiconductive polymetallic sulfides or conductive polymetallic sulfides. It matters wherever you have redox gradients. And should it be that your environment is sufficiently conductive to support this kind of connection, they exist. And I'll end by saying it isn't just a microbe producing nanowires. Bear in mind that when you look at the potential in a sediment, that the realized potential at any point in there is a function of these sort of pseudo-oxidations that can happen. So in other words, oxygen in the overlying water column actually influences the realized potential at a point in space through the conductive nature of the sediment or components in it. I don't know if that exactly answers your question, but I hope that helps.
Okay, thank you, Pete. We don't have time for any more questions for Pete, but catch him after talk.